Couple other logistic things. The office hours tomorrow from 1 to 2:45 are with 107 as well. So I wanted to do some specific office hours for you guys. There's going to be a Q&A session on Monday as well. I'll determine the time of that soon. But if I did office hours tomorrow morning at 9 or 10 a.m., click on which one of these two you would be most likely to go to. Okay, so if neither of them, then don't click in. So click in 9 or 10 a.m. I'll get to that one second. Okay, so then click 9 a.m. if you have workshop at 10. All right, has everyone gotten a chance to respond? Okay, so it looks that's not very useful. I was going to go with the majority. So, all right, I'll try to decide what I'm going to do because maybe I'll do like 9 to 10:30, something like that. That way I can overlap with both.
Usually tomorrow my office hours are 11 to 12, but because of the meeting, I'm going to have to move on. How many people were planning to come to my office hours tomorrow? Okay.
Justin has his office hours tomorrow as well, and he is primed to help you guys with some of the calculations that you guys didn't do so well with on exam 3 as well. Ms. Tara would be willing to help with those as well. So then that brings us to the next point about workshop. Workshop is not required tomorrow. Don't have to go. However, Rafi, Vanessa, and Keith are preparing to help you guys work through the most difficult material from the exam last Friday. I have prepared with them a worksheet. The 3 lowest exam questions, our average in the last exam was a 61, and that was after generously weighting the scratch-off. The range was extreme. It's the biggest difference between high and low that I've ever seen in this class, and people were spread all over the place. If those concepts and the calculations didn't make sense to you, I would highly recommend that you take advantage of the structured practice time tomorrow and go work with your workshop leader. There were 3 short answer questions that had below a 50% average. That tells me that you guys aren't comfortable determining when it's an acid, when it's a base, how to use Ka versus when to use Kb. If you have Kb, do you use Kb or Ka? Is it a buffer? Is it not a buffer? Is it a weak acid? Is it a strong acid? Those are all things that you guys showed me through your answers. You guys are not comfortable with determining, and hence, if you don't know that, you can't solve the problem. So I have your exams. I'll give them back to you at the end of class today. Make sure to grab those before you leave. But the scores are posted last night, and if you feel that you were unable to perform well in the exam because of quantitative skills, the calculations that go behind titrations, not just the concepts, that is exactly what I want tomorrow's workshop to be all about. So we have a worksheet I specifically designed for them to use and implement. They're going to practice on it tonight, and then they're going to use that to help you guys tomorrow. So how do I deal with this? Right? How do we deal with this? I want you guys, these will be on the final exam as well, the quantitative questions about titrations. So instead of just saying, go figure it out on your own, I'm trying to structure some help tomorrow. In addition, what I think is the most fair, because that was really bringing back limiting reagents from first semester and having you guys apply it, and we didn't spend as much time in class as you might have wanted. We're not going to go back and do that. Tomorrow's your time to practice that. But to motivate you to do well in the final exam, what I think I'm going to do is there would be 3 questions that are similar to the lowest scoring exam questions on exam 3. If you do better on the final exam than exam 3, I'll give you back half of the difference between your percentage. So let's say you got 10% on exam 3 on that one question, and on the final exam you get 80% of the points for that question. I'll make your exam 3 10%, I'll make up half the difference and get you back. That doesn't interfere with the exam replacement policy at all. This is a way for you to motivate you guys to specifically learn the quantitative skills that you did not show. A lot of you didn't show you were able to do on exam 3. What questions do you guys have on that? So I want to motivate you not just as a blanket. If you do well in the final exam, it'll replace your lowest exam score if it's higher. But specifically those questions, I'll go in and I'll alter your exam 3 score.
What if we already did fine on those questions and it doesn't affect us?
And that's fantastic.
Whoever.
Yep. So it doesn't bring you up if you already did really well. Don?
And not as far as this, but just the final exam in general, we have a lot of material to,
There's a full semester.
as far as, is there anything that we should be focusing on for the final? Or topics, like can you lead us to topics we should focus on other than type?
So the final exam is cumulative. It covers all the topics of the semester. If you go into it and the previous exams will be somewhat of a guide as far as what we emphasize in our class. The learning objectives from each class are also a really good thing to go back to. There's a lot of them, but at this point that's kind of a good study guide. Sapling are always good. All the previous sapling assignments are now open as practice. So I think that's something that you need to think about and filter through. I'd say the new material from this week and a little bit of lecture chem will be 15% of the exam. But it really does tie everything together from the semester, so keep that in mind. Sabrina?
So the short answer question about titration, like can we expect to have to do like the same exact calculation?
No, not the same exact calculation. You need to show you master the concepts to figure out what type of solution it is, and then how we find the pH. Whether that be a titration, whether that just be a solution, whatever that is, that the 3 questions that maybe you want to look at the 3 questions you did worst on a short answer and make sure that you can do those. Ms. Darrow?
Along with going back to look at all of your exams and seeing where you might have had some knowledge gaps. So maybe you didn't understand something quite well. Taking a look at that and understanding what happened, I think is going to be a really big key for you to do better on the final.
All right, last question and move on.
Like how many questions are on the final? And like how many is like?
So imagine our normal exams are 2 hours. This is a 3-hour exam, so it's scaled appropriately to that, and it represents the entire semester.
So like half of it is short answer and half of it is.
Yeah, it'll be similar format. There might be a little bit more multiple choice because I still only have Justin to help me grade, so there's that limitation. All right, so any more questions, follow up with Canvas discussions, or see me after class. Okay, so with all this said, I don't want to be too doom and gloom. I think we've had a pretty awesome semester. I really want to thank you guys for all the effort you put in. I think that class has been really willing to try to think about the concepts, to try to build those things within your own knowledge, and I think that you guys have done a really good job for the most part on that. So it's been a fun semester. I also wanted to thank Ms. Terrell for being part of our classroom. She normally isn't. Normally we don't have that luxury of having preceptors in the class, and she has been fantastic to be here with us. You'll also notice that we have an additional observer today, so Dr. Goodry is in the back. He is observing how I interact with the class and how the class runs and all this kind of stuff so that I can reflect on my own teaching and improve my teaching as well. This is another forum as well as the student evaluations to have a professional come and say, these are the things you're doing well, these are the things you need to improve upon. So don't mind him back there, but I should mention that we do have an observer today. All right, so I want you guys to answer some pretty straightforward questions, I believe. That'll kind of help us tie together some of the concepts of the semester. There were some like that in the last exam. Okay, so Demetrius, can you tell us about photosynthesis and CO2? How does photosynthesis tie into CO2?
Since CO2 plus light yields oxygen and something else, so it'd be a reactant.
Okay, so who remembers the actual relationship, the full relationship? Chase?
It's 6 moles of CO2 plus 12 moles of H2O equals 1 mole of C6H12O6 plus 6 moles of oxygen gas and plus 6 moles of H2O.
Okay, so I would absolutely want you guys to know this equation and to balance it. And the really big thing to keep in mind is that when we're building plants or building trees, CO2 is a reactant of ours. So then let's take a look at the alternate one that you guys have in question number 2 in your worksheet, right? So in combustion, when we're burning any type of fuel, fossil fuels, biofuels, biomass, CO2 are a reactant or a product there. Everybody in? So our majority says that CO2 is a product. Why? How do we know that? Javante?
reactions always yield H2O.
There's a very big qualification there. What is it, Shane? Okay, so we can have hydrogen as our fuel source. Do we make CO2 from hydrogen as our hydrogen plus oxygen?
No.
Okay, so with the caveat that if we have a carbon-based fuel, then we will generate CO2. That carbon will get broken apart from all the other atoms, and that carbon will recombine with oxygen and make CO2. So we have whatever our carbon-based fuel is, plus oxygen gas. All that carbon will become CO2, or, okay, we can get technical, we make some carbon monoxide and some other byproducts as well. But for the simple case, we can say it's CO2. What does all the hydrogen become part of, Tatiana? If we have hydrogen in our fuel, what does that become part of? All hydrogen that we start with will end up as part of water. All right, so let's kind of tie a lot of the things back together from this semester. Based on what we know is going on in the world, which one of these, oops, this is not A through E. Which one of these statements is accurate? And we should probably do this with, which of the reactions should we do? Let's do photosynthesis. We have two reactions, right? The directionality plays a very large role, and they're the reverse of each other. So let's say for photosynthesis, which ones of these apply?
reaction that I have written down for photosynthesis was different than the one you had on the slide. I thought it only went one way. You had a double arrow one.
All right, so Dawn has a question, a point. What was your point?
The equation you had written down on the slide for photosynthesis wasn't exactly what I had on my paper because I only had it going one way.
Okay, so I really like that Dawn is pointing out, is photosynthesis a reversible reaction? It's pretty much a one-directional reaction, right? We take in CO2 and water and we generate these things. So then why did I draw it like this?
You had your glucose written differently too.
Yeah, so CH2O is the building block so we can make cellulose instead of just glucose. So that's why I had it written as a repeating unit of that. So I'm just going to write glucose here. So why would we have these arrows? Michelle?
Because when you're metabolizing the plant that is photosynthesis, that gets broken down and I can't remember. I know that we learned there's a phrase for that. I just can't. Yeah, that.
So what is KEQ for this? Brooke, what's KEQ for this reaction? I want the expression.
So it would be O2 to the power of 6.
O2?
Oxygen. Or the concentration, sorry.
Okay, concentration of O2 to the 6th power times?
The concentration of glucose.
Okay.
Over the concentration of H2O to the power of 6 times the concentration of CO2 to the power of 6.
So how do humans influence this equilibrium constant?
Or adding more CO2.
Let's actually write one more part of this. How do the rate constants, the forward and the reverse rate constant of this work? Which one would be the rate constant for photosynthesis, and which is the rate constant for combustion or respiration? What would be on the top? What's on the bottom? Right, so we know that the rate constant, is it the forward over reverse or reverse over forward? Salma?
Is there aspiration on top?
You guys think so?
I don't understand the
What
question.
about respiration versus combustion?
We have a forward reaction, and there's a rate of that. There's a reverse reaction and a rate of that. So what goes on top, what goes on bottom? Do you remember how the rate constants relate back to the equilibrium constant?
Doesn't photosynthesis go on top because it happens first?
So the rate of the forward reaction, rate constant of the forward reaction over the reverse. And I'm going to write combustion, I think, instead of respiration, because we're talking about the whole planet, and metabolism isn't necessarily the biggest production of CO2, that combustion is a much bigger version of that.
Why did you just write that? I don't think I understood your question.
So, if we go back to exploring the relationship of our equilibrium constant to the forward rate constant and the reverse rate constant, do you remember what's on top and what's on the bottom?
No.
Okay. Refresh that before Monday. Does anyone remember? What's on the top, what's on the bottom? Okay, so let's think about it. Let's see if this makes sense. KF over KR. So let's, Clyde, question?
Why is H2O in it?
Huh?
Like, isn't there not supposed to be liquid?
You're talking about this?
Yeah.
So water is a reactant. It's not just in liquid. So this would be like KC, we would include it. KA, we don't. That's what you're getting at. So let's think about this. If the forward reaction happens faster than the reverse reaction, if that rate speeds up, that rate constant increases, are we going to have more products or reactants? We're going to push it towards more products, the bigger the relative forward rate constant is versus reverse. Right? So if this number gets bigger, K would get bigger, so this makes sense. So I want you guys to rationalize that out and just try, plug a couple numbers in. Well, what if the forward rate constant goes to 10 and this is 1 instead of 1 to 1? We would end up with more products at equilibrium than we started with at a lower rate constant. So then let's look back at these questions here. Human activity, what's changing? Are we increasing or decreasing photosynthesis? Why are we decreasing it, Lon? What are we doing to decrease photosynthesis? Okay, and how does that relate to photosynthesis? Pauline?
Deforestation?
So we're getting rid of a lot of things that are producing oxygen and glucose that need to use CO2. So this is getting smaller. What's happening to our rate of combustion over the last 100 years? How has it increased over the last 100 years?
Use of fossil fuels.
Yeah, it's been an exponential increase in use of fossil fuels. We're now more efficient at pulling them out of the ground. They're cheaper than ever, so we use them to drive big trucks, to take vacations, to power our cities with clean coal. No one cares if it's clean, it's still producing a lot of greenhouse gases. So this is getting larger and larger as we find more ways to use that. And let's think about larger than what? Let's think about before the Industrial Revolution. The relative level of CO2 was fairly constant. We had some fluctuation, but overall it's fairly constant. If you look at a graph, the ones that we've shown a couple times in class, that over the last 800,000 years, concentration of CO2 over 0 to 800,000 years from when we started gathering, or now we can check this data, kind of has a cyclic nature. And this is 300 parts per million. And this is about 200 parts per million. So the max before was about 280 in the previous cycles. I think there were maybe 2 more peaks. You guys know what the current CO2 concentration is, Alex?
Yes, like 400.
Has anyone looked at it in the last few days?
It's higher now.
Yeah, so I think it passed 400 in spring. I think now we're, so that's like up here, and we're still going straight up. And this point right there is, when did that start skyrocketing?
The Industrial Revolution.
Yep, about 1890, right, the Industrial Revolution. So then, which of these answers is right? Is KEQ getting larger? It's a constant, right? It doesn't change. Unless you change the rate constants. So, I think the clickers are still open. Go ahead and click in what you guys think, which of these are accurate.
Oh.
You can enter 1 and 2, would be 12. All right, is everyone clicked in? So a majority of us are saying 2 and 4, but not a huge majority. 4 and 2, okay, so we got another 6%. So if the forward rate constant is getting smaller, the reverse rate constant is getting bigger. So forward is getting smaller, so that's number 4. And then if that happens, what happens to this fraction? Smaller number over a bigger number. Does that mean that k is getting bigger or smaller?
Smaller.
It's just getting smaller. So I agree with you guys that k is getting smaller due to human activity. And that's because we're drastically decreasing the amount of forests that there are in order to photosynthesize. And we're significantly increasing the amount of fossil fuel production in a relatively short amount of time. Extremely short if you compare it back to the scale of the globe. We've never had concentrations this high in the last million years. All right. Saw something the other day that there's one of the newest Air Force or the Navy vessels is actually powered by biofuels. It's kind of cool. So, is burning fossil fuels as bad for the environment as any other carbon-containing fuel like biofuels? So talk to your neighbor, what do you guys think? And why? I want to hear some good explanations for why. All right, so the majority of you guys say that this is false. So who would like to argue their case for why it's false? Natalie, what are your thoughts?
You said false because maybe some fuels don't burn, don't produce carbon dioxide at the same rate, like maybe some are slower.
Okay, so there might be something about the rate of production of CO2, but if we take a molecule with 10 carbons versus 8 carbons, typically when we burn them, we're going to need more of the one with 8 carbons to make the same amount of energy. What other ideas do you guys have? Javante?
I said false because if you're burning fossil fuels, you're taking that out of the ground that's not already active, like in the carbon cycle, so you're adding more CO2, like you're increasing the concentration of CO2, as opposed to just because something produces CO2 doesn't mean that it wasn't already part
So we could argue that fossil fuels are part of the carbon cycle. What makes them so different from where we get biofuels?
You have to dig to get them, like you're adding it.
Okay, so maybe it takes more energy to dig in and get them. Claudia?
Don't you get biofuel from like corn and things like that?
Get them from what?
Like crops?
Yep.
So you're not really digging.
Okay, so there's the digging part of it, right? There's the expenditure of energy to dig down and get them.
I was gonna say, just to elaborate on what Javante said, when like fossil fuels, they're like when he's talking about the carbon cycle, they've been taken out, like they've been underground and they're like stored there. They're not part of the cycle of like concentration of carbon dioxide in the atmosphere. But when you're growing biofuel, the plants are taking the CO2 from the air and you're releasing that same CO2 back into the air, so it's not changing the percent composition of the air.
Anyone want to add to that? Don?
So I was gonna say, when you burn fossil fuels, aren't you adding other greenhouse gases, not just CO2? So isn't it worse?
Okay, so there's a lot of impurities. There's a lot of sulfur and nitrogen impurities that when you burn, make acid rain, and there's a whole bunch of other stuff that goes along with that. And I really like the way that you guys kind of brought this back around, and the time scale is really one of the most critical components here. That how long does it take for CO2 to become fossil fuels? I mean, the term fossil is in the name, right? So millions of years? How long does it take for CO2 to become available for biofuels? One growing season for seeds. For some of the bigger plants, maybe a couple of years to grow them and then to have the seeds available, or the corn or whatever else. So the idea is not that biofuels are the answer to everything, but that just because something is a carbon-based fuel doesn't mean it's equally as harmful to the environment to burn it. And this idea of clean coal or clean carbon can be very misleading because it totally ignores the time scale that everything is built on. That if we took a whole bunch of land and we planted things in order to grow biofuels, we would constantly be pulling CO2 out of the atmosphere to grow that. And then we can release that back again when we grow it, but it's much more sustainable to have a cycle that's on a shorter time scale, which I think was one of the main things Javante was trying to get at. Versus fossil fuels, do you guys want to start a business where we're going to grow fossil fuels and we'll harvest those when they're ready?
No.
Why not, Chase? Not only will you be dead, but
I'll be a fossil.
the human race will probably be dead by the time that fossil fuels will be ready to harvest. All right. So let's keep that in mind. And I do want to have some questions on the final exam that show that you guys can reflect our role as it relates to CO2 concentrations in the atmosphere and how that influences climate on the planet. You had some on each exam, and there will be some of those in the final exam. So let's go back to the question that we ended class on Tuesday with. I asked you guys to try to work through these calculations on your own. So go ahead and click in what you determined, and we're going to have a discussion about how we would go back into how do we find equilibrium constant for a particular reaction when we have this information in front of us. So take a minute, bring out your paper, talk to your neighbors, make sure you guys can explain how you got through it, and then we'll talk about it. A lot of times when you see killa or milla, I would just really insert times 10 or whatever it is there, and that's much more efficient.
Wait, I just heard the same thing. Yeah, negative RT times R. So the delta G equals negative RT times ln of K. So it's R 8.314 or T is 298. So it's negative 8.3. And what is the There's no N. It's ln. What's K? So we're fine. G is negative 30.5. And then you got that. Negative 4.1. Oh, yeah. Okay. What'd you get? Oh, negative 1.01. You're right. And second. Yeah, 1.01. Oh, I got a little bit higher. Which is 1.01. Okay, because Randy was in here last time, so couldn't get it going.
All right, so let's talk through this. What way do we have to relate Gibbs free energy at standard conditions back to our equilibrium constant? Salma, how would we do that? Do we have a relationship between those two? What relationship is that? So Gibbs free energy at standard conditions, that's delta G naught. That's that little zero. Okay, so instead of saying equation, I really like to emphasize that there's a relationship explained by a mathematical equation. So we know the relationship between Gibbs free energy at standard conditions and K. What is that relationship? What's that equation? Almost. What are we missing? What are we missing, guys? Kier? Delta G naught. This is only true at standard conditions. If we have anything but 1 molar concentrations, then this is no longer true. How would we find this if we had non-standard conditions? What is delta G? We're not going to use it right now, but what does delta G equal? Something similar to this, but there's more to it, right? Alex? Okay. So if we ever say Gibbs free energy in non-standard conditions, we have to remember that where we are compared to equilibrium, Q versus K, is something we have to take into consideration. So that Q, what is Q when we're at standard conditions? 1. So ln of 1 is 0. So that's why at standard conditions, delta G naught, that's what we call it at standard conditions, is equal to minus RT ln K, because this whole thing becomes 0 at standard conditions. Okay, so we have the relationship. We have the equation. Gibbs free energy at standard conditions is equal to minus RT ln K. What is R? Salma, you want to keep going? What constant? Megan? It's the gas constant. What's the number and what are the units of it? Close, okay. And then what are the units? Is it liter atmosphere per mole Kelvin? Do you want liters? What units do you want for Gibbs free energy? What do you want to have and to cancel out? You want joules. So it has to be some form of the gas constant that has joules in it. Chase, what are units?
Is it moles over joules?
So it's joules per mole Kelvin. 8.314, whatever. This is a shortened version of it. So we really want to pay attention to the units, and I want to see everyone, when you do this type of calculation, write out all the units because it's going to be really important. Because if you don't write that out, you're just going to write 30.5 equals minus 8.31 times T times natural log of K. Why would that cause such a problem? Why would it cause such a big problem if I went ahead and wrote so delta G naught equals and I found my T and I did this. What problem am I going to run into here? Valerie? So on the right side we have joules, on the left side we have kilojoules. It's really easy to do. So please write out all of the units for your gas constant. What temperature do we have here? McKenna, what temperature is this at?
298 Kelvin.
Why do you say 298 Kelvin?
25 plus 273.
Great. So if we look at the units once again of our gas constant, we have Kelvin there. So we need to make sure that it guides us really to say, well, this has to be in Kelvin. Megan, are you changing your answer? Okay. And then we can kind of plug all this in. The way that I saw a couple people doing it was trying to write R in terms of kilojoules. I really would advise away from that. I'd really advise you to put everything in joules. That little kilo right here for kilojoules, what does that stand for? What do we do when we see a kilo? Multiplied by 1,000 or 10 to the third. So that's all I did right here, is I kept it in joules, but I replaced kilo with 10 to the third. Okay, so is our equilibrium constant 12.316? Okay, so I'm going to give you guys another minute to click in what the value for the equilibrium constant is. So whenever you see kilo, just put 1,000 in there. Place it in. All right, a couple more seconds to go ahead and click in your answer. Jose, how do we go from ln of k equals 12.316 to finding k? Close. So he suggested 10 to the, if it was log, that would be absolutely accurate. But it's ln, so what do we do? E to the. So if we do e to the 12.314, that gets rid of our natural log. So we have 3 sig figs. It looks like the top answer is that. All 19%. And then we have one way down here. So what happened, guys? Where'd you guys get stuck? Where'd you get and had a hard time getting past? Michelle?
I think I did everything right. I did it twice and I got a really weird number the second time, so I did it wrong. The first time I did it, I got the 12.316 for the LNK. And I guess I put it in my calculator wrong and I got some really weird number.
So order of operations is going to be really important. Making sure we keep that negative sign for minus RTLNK, and we have a negative 30.5 kilojoules. We got to make sure that kilojoules, we hold on to that, so that's times 10 to the third instead of kilo. And then that last step of e to the. Is that something we're not so comfortable with, natural log and logs? Okay? Suggestion, work on some practice versions of that. On your homework, it has a couple where you have to go back and forth between Gibbs Free Energy and K and E cell. So I'll have you guys kind of work through that. So let's go ahead and draw a Gibbs Free Energy diagram of what this reaction would look like. You guys already know these details. Go ahead and draw a Gibbs Free Energy diagram. What is this going to look like? draw on here? And explain why afterwards.
Yeah. I don't. For this right here, why does it have phosphate listed as PI instead of PO4 and 3
It's just the way the biologists write it.
Oh, okay. I'm just curious.
Fair question.
At least I
And it
know
should
that.
have water on the left side too.
Right.
No.
This pretty sucks. All right, so Jose drew his Gibbs Free Energy diagram up here. Can you explain to us why you drew it the way you did, Jose?
Basically, A dot is so big, it's essentially saying that it's closer to products than it was to reactants.
What's closer to products?
Equilibrium.
Okay, so can I have someone else say that again another way? So what does a large K tell us? Pat, I heard you and Pauline discussing this.
That the reaction's in a favor product.
That when it gets to the most stable mixture of reactants and products, we're going to heavily favor products. So I like the way both of you guys said that. I think they synergize with each other. And so what is a dotted line?
Where the equilibrium is at.
Okay, so the equilibrium is much further towards products than it is towards reactants. So Thomas, I heard you asking a question. Where's Q? Where's Q here?
Standard condition.
Yep.
Q is 1, so it's right. I think it's right where K is.
Does everybody agree that Q equals K at standard conditions? McKenna, why are you shaking your head?
Because Q equals 1 at standard conditions,
And where is that?
right in the middle.
So at standard conditions, Q equals 1. That means you have an equal mixture of products and reactants. That means we're right in the middle. So did someone use delta G instead of K to draw the diagram the same way? Did anyone use delta G naught? How could we use delta G naught to draw this diagram? Alex?
We know based on that's spontaneous.
Okay. Spontaneous in the forward or reverse direction? How do you know it's spontaneous in the forward direction? Great. So having a Gibbs free energy at standard conditions tells us that when we are at Q equals 1, when we have an equal amount of reactants and products and they're all 1 molar, we know that the reaction is going to go from there and go towards more products. So that means that the reaction lies to the right of Q of 1. Either one of those ways would have been totally legit way of justifying how you draw this Gibbs free energy diagram. Any questions on either one of those two? Can you guys calculate E cell? How would we calculate E cell for this reaction?
It's the same calculation you would use for delta G naught, but it's RT over N, which is number of electrons, or number of moles of electrons, F times ln K is E cell.
Okay, so we could go from K that we calculated to E cell. Could we go directly from delta G naught to E cell? If we knew the number of electrons. We would need that for either of the ways, right? So we have E cell at standard conditions equals, what is the one you said, Bree?
It was RT over NF times ln K.
Times ln of K. We have K, so we could calculate that. Or, what's the other one? Well, so that is that one, right? How do we use delta G naught, though? Can we relate delta G naught to E cell? Michelle?
Wouldn't it just be delta G naught over the number of electrons times the constant?
So the equation, let's go back to the equation you're pulling that from, equals NF. Is this the equation you're rearranging? Okay, so if you go back to that triangle, there's a whole bunch of different ways to go interrelate between these three, and you can use any of the directions that you want. They're all fair. Just have to rearrange our equations. So this is the kind of question I expect you guys to be able to answer. This, I'm not opening this because we already talked through it. Is if you have a Gibbs free energy value at standard conditions, does the reaction lie to the right or to the left? If we have E cell, if we have K, and you can answer those a number of different ways. So this is the diagram that I drew. Standard conditions, our Q is right in the middle. We can say the reaction lies to the right because we know it's standard conditions. Okay? But we don't always have standard conditions. So what if we had a 10-to-1 ratio of reactants, 10 reactants to 1 product? Where would Q be on your diagram? Go ahead and draw where Q would be on your diagram if we had, instead of Q equals 1, we had this ratio of reactants and products.
It's not delta G naught anymore, technically. This Q's not equal to 1.
So where's your new Q?
I wrote it.
What do you mean? So this is your K?
Yeah, I know. This wasn't supposed to.
Oh,
No,
that's okay.
Isn't that right for the question we just had, though?
Yeah, this looks great for the question we just had. So the question now is, well, if we have a 10-to-1 ratio, where would the new Q be? Is it going to be here? Is it going to be there? Is it going to be the same place? Okay, everyone click in their answer of where it would be, left, close to the middle, or to the right. So most of us are saying it would be left of the middle. Why, Dan?
Because there's a lot more reactants than products.
Okay, and the left side is reactants, right? So I agree with you guys. Then the next question is, so that's our Q at non-standard conditions. So then what about that exact same condition, right? What would the relative sign of delta G not, sorry, that's terrible, of delta G be? And we're comparing that to the sign of delta G at standard conditions. I hate how standard conditions is referred to as not, because then you're like, not that, but not.
I'm sorry, can you?
So read the question. Hopefully this refers to the Q that we just drew on our graph, the one that's on the far left side there. What are you thinking, Alex?
Based on what we look at the line that's both negative, so negative.
So I want you to think through the wide world. I'm not going to justify it relative So get out of that and start thinking well, delta G naught is Q as well. What is Q for that? Think about the sign for when Q is 1. All right, has everyone clicked in? Did you guys all agree? Wah, wah. All right, who wants to argue their case? Thomas?
I think because if you do a count of the decimals, it's going to be negative. So negative times negative positive.
Okay, so you're getting into the math part of it. and ln of, so what is your Q value now? What is the numeric value of Q here? Is it 10 to 1 or 1 to 10?
I thought it was 1/10.
Okay. But here's the thing, is we're comparing it to K. We're not saying by itself what is Q. We're saying what is Q compared to K. So can I get someone else to argue their case? Cosme?
I said it doesn't change because K doesn't change.
Okay, so K doesn't change, so no matter what Q is, delta G will always be the same as delta G naught, the same sign?
Well, I was just getting that delta G naught is going to be the same
Why?
because it's based off of K, not Q.
Okay, so it's not just based off of K. That's part of it. Sabrina?
Well, both of the, like, the Q that's closer to the reactance and delta G naught are both on the left side of K, so that they both, like, move towards K and, like, release energy, so they both have a negative sign.
Okay, so we're so close. So 1, K doesn't change. 2, Q changed, but they both went the same direction away from K. So that for the reactions to reach equilibrium, what direction are they going to go? Towards reactants or products? Or is it going to be different for the two? To get to equilibrium, will this reaction go more towards products from where it starts at Q? Or will it get more reactants? This reaction will go to the right to reach equilibrium. That means that it's what sign for delta G? Negative delta G. What was it for delta G naught? It was the same, right? We started here instead, but we were still going the same direction. So the sign of delta G and delta G naught, in this case, they're both more reactants compared to products versus equilibrium. So they're both going to be shifting towards products to reach equilibrium. So these both have the same sign. Does that mean that they're identical? So let me ask the next question then. What about the magnitude of delta G compared to standard conditions? Is delta G going to get further away from 0, even more negative, or is it going to be less negative, closer to 0, even though it's the same sign? It's going to happen to the magnitude of that number. I couldn't do these without. It would answer your previous questions. It's not. We're thinking through it. Thinking through it. So delta G is, we'll actually get to that in 1 second. I'll show it. All right, so go ahead and click on your best guess. Closing out. We're split. Can anyone try to justify their answer? Shane?
I did a calculation, it's more negative, but you take the, like you said before, if you take the ln of a decimal, it's going to be negative, so negative minus a negative is even more negative. That's one way to look at it. But also, if you're further up the curve towards the reactant side, you have even further to go, so the number has to be larger.
So I really like that last description. So if you think about this is how much potential energy is there that's being transferred during this process. If we start, let me use a red pen. If we start at standard conditions, that's where I have that big red ball. To get from there, and remember our y-axis is Gibbs Free Energy. So that means to drop down to the level of equilibrium, there's not much of a drop it's going to go as it moves to the right. If we're at Q of 1/10, how much is it going to be more or less potential energy transferred? It's going to go down all the way to there, so that means that the drop is actually significantly bigger. So that's why I really like these potential energy diagrams, is because it gives you a visual. If we just release the ball and we're further away from equilibrium, we're going to have more potential energy to transfer to another reaction. And we can calculate that, and we're going to get into that in a minute. So if we go back to here, delta G would become a larger negative value further away from 0. There would be much more energy that could be transferred. So let's try to take that reaction and use it to drive this reaction here. How much energy is left over if we're at standard conditions, right? Not ideal conditions, but if we're at standard conditions. Standard conditions for everything. This is how much energy can be used, given off, right? This one needs that much. So how much energy is left over? You find the difference. You need 15.
I was sitting here doing like the huge, like the ln and everything for both of them, and then subtracting that, and I could figure it out.
All right, let's do another 20 or 30 seconds.
Why is mine saying
All right, closing out. All right. So, Don, can I have you explain conceptually what we do with this, how we solve this problem?
So apparently it's a lot easier than I thought it was. And you're finding the difference. You said the first one, the ATP plus H2O, needs, or gives off negative 30.5 kilojoules, and the second reaction needs the 15, so you're subtracting the 15 from the total that you have.
And we're finding how much is left over, what the excess energy per mole of ATP that is used per mole of glucose. So that per mole is really important. That's kilojoules for every mole of ATP that are yielded, kilojoules for every mole of glucose that are needed to phosphorylate that. And so is the sign important? Is that equals, or is that, it's really hard to see is that a minus or equals? That's, okay. So we have to make sure that it is still negative. That means it is going to be spontaneous. Or equals. What's that?
I think my number is on my sheet.
So let's take a look at these guys here. Which of these reactions throughout all of oxidative phosphorylation, glycolysis, could be used or would require the input of ATP in order to go at standard conditions? Talk to your neighbors. Try to figure out which one of these require the input of ATP specifically to go at standard conditions.
The equation with Gibbs Free Energy is related to Gibbs Free Energy standard conditions? Yeah, I did that last time.
Like, you would have to add the ATP in order to change the sign of the other delta G that makes the reaction.
This is delta G naught. So that's how we find Gibbs Free Energy. Sorry, I thought we were getting into it, but I remember it was for all its parts. Okay, so click on all the numbers that would need. Am I saying backwards from what it's asking?
What is it asking?
Which of the following reactions could be used to produce ATP at standard conditions? Is that what you guys are clicking in, or are you clicking in what I said?
I clicked on what you said.
Okay, so you're clicking in which ones would need ATP to be driven forward? Is that what you're clicking in? Okay, sounds good. So which one of these, McKenna, how do we decide which one of these would need ATP to be driven forward?
I was reading it wrong.
Chelsea, you want to help out? So if they're negative, do they need help to go? At standard conditions, if it has a negative sign, they're probably going to go spontaneously. So Sabrina, which ones would need ATP in order to be driven forward? 1 through 4, 7, 8. All of these guys. Which ones would we be able to use to produce ATP? So let's go ahead and say, so I think for the question that I just asked, I agree with you guys here. And then the question that's on the screen right now, which of the following reactions could we use to take ADP and phosphate and make ATP? Could we use to store energy?
Whatever we didn't use.
You said 5, 6, and 9, and the first thing that I thought of was Betty Bob. I don't know why.
Let's do another 15 or so. Pretty wonky with the numbers all over the place. Sorry about that. All right, closing out. So Tatiana, can I have you describe how you looked at these and determined which one of these we'd be able to use to generate ATP from ADP? Okay. Is that true that all of these could be used to generate ATP? Brian, what are your thoughts?
Yeah.
Why?
That's the reverse reaction of what we just did. Because we're producing ATP now.
So, how does that line with these numbers?
Well, we had like a positive delta G naught reaction for our forward reaction, right? So, and reverse reaction it would be negative.
So we have our delta G down here. Delta G naught is negative for ATP to ADP. So what would the sign be if we had the exact reverse reaction? Why positive, Joante?
It would require energy.
So that's kind of a nice key to keep in mind, right? That if we have the forward reaction and it lies like this, the reverse reaction, what does it look like? Literally a mirror image because it's the same exact thing. So if we're trying to take something and drive it to here, it's basically like saying, well, how likely are we to be able to go up that hill? Do we need energy to do that? We need to take a couple of reactions that are that give off a lot of energy and use those in order to drive this reaction forward. So I agree with you, 5, 6, and 9. Which of these reactions could be used to generate NADH and H+ at standard conditions? Take about 20 seconds to click in your answer. And we're closing out. Kirk, which ones of these could we use to generate NADH and H+? None of them. Why?
I don't know. I didn't have time to think about it. I just know this is the answer.
Shane, I think you have the simplest answer of all. Everyone see Shane's answer? Okay, so do any of these at standard conditions generate 61.8 or greater kilojoules for every mole? No. Does that mean that we never, ever, ever generate NADH plus H+? So then what are we missing? What's the key piece of information? We know that that happens, and it happens during glycolysis. So what are we missing? Talk to your neighbor for a second. What are we missing? It happens. It happens with these reactions. So why does it not look like it from this table? What are you guys thinking? Thoughts?
It doesn't just use like one reaction, we need more than one.
So it's really hard to tie together two reactions to make something happen, to make one product. So there's something else major. So what ideas do you guys have? Why does it happen and it doesn't look like it does right here? What are we missing? Demetrius, what are we missing? So that's kind of cheating. We can't really take 2 times any one of these reactions and use it. So it's something else. What is it? What else are we missing? What broad, sweeping generalization did we make with these?
They're at standard conditions.
Is everything in the body at standard conditions? Okay? So, you guys don't really need to answer this question, right? Is everything in the body at standard conditions?
No.
Okay, so there's this awesome Chinese proverb. Okay, so what we can do is we can look at individual reactions and we can go back and take a look at what is the actual condition and then how does that relate to K. So let's take a look at this. If we have Gibbs free energy, this is an equation that we used at the beginning of class on, actually you guys used it last week I think, right? RT-ln of Q over K, RT-ln of Q minus K. So if we're at standard conditions, what happens to that equation on the right? If we compare normal to standard conditions, what is this right here? So if we want to find actual Gibbs free energy, isn't that just RT ln of Q minus Gibbs free energy at standard conditions? So if you guys knew Q, could you find the actual Gibbs free energy? So I have these all worked out where you can see exactly what we just did. But really the key is if we know Gibbs free energy at standard conditions, we can look that up in that table we just had. Well, then we should be able to calculate Q, and then we have the exact relationship that we want. So let's not worry about that. Let's look at one of these specific reactions. What is Gibbs free energy at non-standard conditions? Can you guys figure this out? So I'll hang out for a few minutes after class. We have 1 more minute of class. Before you leave, at least set this up. I don't want to see your calculations, but I want to see if you can set this problem up. How do we use what we just learned to find Gibbs free energy at non-standard conditions like these that are described here? Okay, after, okay. Just after 1 more minute for class.
I don't even know like where to begin right now.
So what was the relationship that we just had that was another version of this that compares Gibbs free energy at standard conditions and non-standard conditions? So what is delta G naught? What does that equal in relation to this?
So is it plus 50, negative 55?
Minus RT-ln. So this right here is delta G naught.
Okay.
So we have RT-ln of Q plus Gibbs free energy at standard conditions. So if we have Gibbs free energy at standard conditions and we know Q, we can find delta G. So as you guys finish, feel free to head out. I will be in ICE 314, the Learning Center, at 9 a.m. tomorrow until 10:30, and then again in the afternoon. Feel free to come with questions for this. I'll also hold Q&A session on Monday. Justin's office hours and Miss Terrell's office hours are tomorrow. It's been a fun semester, guys.
Are you going to a test? I'll be there in like 20 minutes. Yeah, we have it. I'm gonna wait, no, we're going to Are you going back to